Who did verify Strassen's decomposition? Did anyone go and do this? Like this rank 7 decomposition of the Mammut 2. Did someone verify it? You verified. How long did it take you? How long did it take you? Yeah, that was kind of what I took me half an hour to do. Yeah. Okay, good. Yeah, so you know, if you have half an hour spare, you know what to do. Okay. Well, the other exercise we're not going to discuss now. I brought my computer today, so you know, in case I'm too slow, at some point I will just switch to some slides and it goes faster. I think Matthias did the opposite way around. It saves kind of time. But anyway, I want to do Blackboard. I think it's more fun. I hope you can read my writing. It's not the best, as you've noticed. So a little summary from last time. We discussed that the GHZ state degenerates to the W state, all right? And we also discussed that the W state restricts to the EPR state and to the EPR of AB, and it also restricts to the EPR of BC, and it also restricts to the, oh, that must be AC here because it's in the middle, and this is EPR of BC. All right, and then we have discussed that down here we have the product state, and the product state has many different names. Quantum information people like to call the unentangled state. The computer scientists like to call it a simple tensor. Some people call it a decomposable tensor. It has many names, but maybe it's the simplest is the product. Okay, this is all you need to know about 3 qubits in one graph. I think it's quite nice. You have this hierarchy, and there are no more relations than that. Of course, all of these you could also write degenerations. It would also be correct because restriction implies degeneration. So please do remember that. All right. Then, of course, the question is, how do we show that the W doesn't degenerate to the GZ? Okay. And I want to discuss that a little bit. But before I discuss that, maybe let me remind you of this definition that we had of the rank of a tensor. That was the minimum. R such that the GHZ of R restricts to the tensor T. Then, of course, someone asked, what about that? That was kind of like the rate at which you, or the amount of GHZ state needed to create the state. So that was kind of like your entanglement cost. Maybe the log of that would be the entanglement cost in this SLC thing. And then, of course, if you have an entanglement cost, how much does stuff cost? Then you also have what's the value of it, how much do you get for it when you sell it again, and that's the maximum over R such that T restricts to GHZ. Okay. And then, of course, you know that now we have weakened this restriction, and weakening restriction, of course, allows you to weaken the notion of rank, and so this is called rank and this is called subrank. Allows you to weaken this notion here, and you can put this one here, and if you do that, then people put an underline here, and they call it the border rank, because you kind of like go to the border of the set, and here you can do the same. You can put a border here, and then you get the border subrank. All right. So obviously, and now this is an inequality sign. Sorry for these many inequality signs here. In the normal inequality signs, because these are 2 numbers, of course, it's bigger than that, and so on. Excellent. Good. All right. Then we are going to discuss now the other direction. So we're going to do this in the following way. We're going to notice the following thing. We're going to define, first of all, we're going to define a group. Here's a group for you. I call the group G, and it's the group of GL, so the linear invertible matrices on A, and the linear invertible matrices of dimension B. It's like a triple of group elements, right? But notice that I'm taking it to be invertible here. And that's the group G. So then if you got a tensor defined in ABC, then what is very natural to do is to look at what people call an orbit. I denote it by G dot T. That's just a set. It's a set of tensors. Namely, it's a set of all tensors T prime that are, in our language, related, that you can obtain by this linear group action, right? Yes? Yes. Why is it true? Because yes, so if you want to yeah, how do we see this quickest? So right, if it was not true, right? If it was not true, we would have the following degeneration. Right? If it was not true, then you would have some numbers. Then you would have that the GHZ of some R, right? The GHZ of R of T would be bigger than it's bigger than, it like restricts to T, and that restricts to the GHZ of Q of T. Okay, so if Q of T was bigger than R of T, then it would mean that by restriction you can kind of increase your GZ state. And we've seen this, that it's not possible in the case of the EPR state. Remember that we discussed it, that you can't go up in the index for the EPR state. I didn't explicitly discuss it for the GZ, but the argument is the same. Okay, so this is like impossible. This is only, this implies Q of T must be smaller than R of T. And by similar argument, you can do the same for border rank. Okay, so I want to define a set. Okay, and you know that kind of like this just corresponds to basis change. We call it isomorphic, the tensors, if they have this property. So this is really just all the T's that are isomorphic. So maybe I should write it like this. It's all the T primes that are isomorphic to T, okay, in our language. Why GL? GL is the invertible matrices, general linear group. Just the invertible A by A matrices are GLA. Okay, so that's just okay. Now, if you go to the now, what you could do is this is a set. It's a set in you know, it's a set of tensors. So all of these tensors are you can think of these as these cubes. And now you can take, just as we took these limit points before, you can, of course, of the entire set, you can ask what is the boundary of it, right? You can go to the limit points. And that is like the Euclidean closure. Okay, so from this, you can go to you can kind of like consider the closure of this. You can Euclidean close this off just by taking all the limit points in addition. And of course, that here, we also know what that is. That is all the T prime such that T degenerates to T prime. Okay. So for us, these two notions, this orbit and the orbit closure, they're very natural things. And this Euclidean closure is really just like, you know, have a set and you draw it on like your, you know, on a piece of paper. And just a bit high dimensional. But so now what we're going to do is, so now there's a little theorem, we're not going to prove it, that if you take this Euclidean closure, or if you take what is called the Zariski closure, they're the same. So in this setup, okay, Euclidean closure and Zariski closure are the same. So, right, the Euclidean so if you think about your normal distance measure, that gives you some topology on the set, on the set of tensors, and the Zariski, there's some other topology called the Zariski topology, and the Zariski topology is the topology obtained by saying the closed sets in my topology are the zero sets of polynomials. Okay? So the zero sets of polynomials are the closed sets. And turns out that these two things are the same. Okay, so it's just sort of like a side remark. What it tells us for us now, this implies that this this closure G dot T is an algebraic variety. Algebraic variety. Okay, and you know, I'm not an algebraic geometer. I don't think many of you are. So we might just kind of, you know, ask someone, what does that mean? And what they will tell you is that what it means is just kind of like what I said with the Zariski closure. It actually just means that GT as a set is cut out by polynomials. Okay, so you can define polynomials on CA, CB, right? CA, CB, CC. Okay, so this here is some, you know, just think of it now as some large vector. Okay, some large vector with, you know, A times B times C entries, and now consider polynomials in these entries. No. Just so an element here, right? Is just you know, now if I flatten it completely, right? It's just like it's just T1 up to, you know, TD, right? Where D is. Okay, just think of it like that. And now you could just you could consider polynomial. Here's an example: T1 squared, T2 squared, T4 to the 5, right? That's a nice polynomial. It's an example of a polynomial, and it turns out that if you've got such an algebraic variety, what you can do is you can, in principle, you can find a set of polynomials in these variables t, such that this g of t is exactly defined by these polynomials as a zero set. Okay, so it means, let me just write it down. It means that, you know, there exists polynomials such that this gt is equal to all the tensors t, such that this list of polynomials, so there exists some list of polynomials, pi, I from 1 to, and it's actually a finite list, to L, such that this is 0 for all I. Okay? Polynomial. Sorry. Oh, L is some number. Okay? There exists some L, some finite number L. We don't know what it is. Maybe 100. Depending on, I mean, the number depends on A, B, and C. Okay? In some completely terrible way, probably. But there is, it's kind of like theoretically, it's nice to know, right? So now I give you these tensors, right? Give you this thing. Someone tells you, oh, it's an algebraic variety, and then you know, oh, right. Then there are these polynomials, and they will cut out. I mean, people in algebraic geometry they cut out this variety. Okay, so it's all the t's that vanish simultaneously for all of these polynomials. That's it. Out of the set of all tensors. Okay. What do you mean? There's no. These are the coordinates. Okay. It's like T1 squared, T2 squared, T4 to the 5, right? It's an example of a polynomial in the variables. Sorry? In the variables of T. Yeah, maybe it's better actually if I do it, let's write T, let's not make it too obscure. So let's write T in this form that we had it before. EI tensor EJ tensor EK. Okay? And then a polynomial, you know, a polynomial in T, and, you know, think of non-zero polynomials. So polynomial in T would be, you know, for instance, you know, Well, I'm going to write down one for you. Hold on. Where is it? I'm going to write a nice one for you. You want to see an example? Here's an example. Hold on. Okay. So, hold on. I need an entire blackboard for this example. So, okay, all right, here we go. Dat of t, it's called the Kaley hyperdeterminant, is the following polynomial. These are my ones. Plus t. Oh, and I guess you want to, all right, you want 1 and 2, all right? Okay. It's now very error prone because my notes say, oh, well, you'll see. Yeah, I knew it's going to go wrong immediately. 1, 1, 1, 2, 2, 2, 1, 1, 2. You'll see a symmetry in a 1, 1, 2, 2, 2, 1. Very good. Thank you. 1, 2, 1. And all squared, okay? 2, 1, 2. It's homogeneous of degree 4 plus t 2, 1, 1 squared t 1, 2, 2 squared. Okay? This was the, yeah, you happy? Does it look nice? Yeah, it looks nice, right? This was the first of this first row of several rows. Minus 2 times. Something wrong? Ah, they're all squared, right. Okay, fine. Yeah, okay. 1, 1, 1. T 1, 1, 2. T 1, 2, 2. T 2, 2, 2 plus, no, minus 2 times T 1, 1, 1. T 1, 2, 1. If you have to go to the bathroom, it's a good point now to do that. T 2, 1, 1. T 2, 2, 2. Minus 2. T 1, 1, 1. Okay. T 2, 1, 1. I don't know if you start seeing a pattern. 1, 2, 2. T 2, 2, 2. Okay. Minus 2 times T 1, 1, 2. T 2, 2, 1. Yeah, I was not going to write it down, but I think it's instructive to see how complicated they are. T 1, 1, 2 and T 1, 2, 2. T 2, 2, 1. T 2, 1, 1. Minus 2. Oh my God. T 2, 1, 1, 1, 2, 1. The last row is a bit different, so T 1, 2, 2. 1, 1, 1. Yeah, you convinced now? You're convinced now? Okay. Well, okay. So whatever, the last term you can figure it out, right? The last one here is simpler. I'm just writing it down now. Okay, plus 4 times. And then you figure out what the last one is, okay? Very good. That's called the Kaley hyperdeterminant. I don't know exactly when Kaley lived, but it was not in this or the previous century. So that's a nice polynomial. And this polynomial has the property that this polynomial cuts out the W state. Okay, so on, for all things, so on this variety, right? So, yeah, on this variety, it just vanishes. Yes, it's nice, eh? It's one single polynomial that cuts out this W variety, and you can see it. You can actually, well, the first thing, of course, you have to do is you have to verify that it vanishes in the W state, right? So, and that's why I wrote it down. The W state you see the first term, the W state is like 1, 1, 2, right? Or permutations of that. So 1, 1, 2, well, it vanishes on this one. Here, 1, 1, 2, it's not vanishing, but 2 to 1 is vanishing, right? So the second term is also 0. Okay, by symmetry, the rest is 0 here. And you look here, oh, that's 0. By symmetry, the rest is 0, right? You see, oh, that's 0. By symmetry, the rest is 0. Oh, that's 0. By symmetry, the rest is 0, okay? So that thing just vanishes in the W state. Go ahead. Yeah, sure, yeah. I didn't say that, but now you can verify that it doesn't vanish on the GZ state. Well, why not? Because the GZ state has a 1 here, and I guess the other terms are 0, and yeah. So it gives you like, I don't know. Does it give a value? I mean, maybe it gives a value 1, or I thought it gives the value 2 of it, but okay. So what we saw, what is easy to see, is that the W is 0, right? And what is also easy to see, that it's on the GZ state, it doesn't vanish. Okay. Okay, very good. Now, it still doesn't imply that it vanishes on the entire W orbit, right? Because I have to show to you, well, that on all the other states it doesn't vanish. Of course, it will. Yeah. So how do we do that? Well, the way to do it is actually to show that the polynomial, because now we have only one here, that the polynomial kind of like transforms nicely under the group G, right? So if what we want to show is that this polynomial on A tensor B tensor C on some tensor is actually equal to the normal determinant of A times the normal determinant of B times the normal determinant of C times that of T. Okay, so if I have that property, and then I know that if it's 0 on the W, then I know that it will vanish on anything in the orbit of W. Okay, so this will imply that it vanishes also on G on W. Okay, and now you notice that polynomials are continuous in the normal topology, and that implies that also it will stay 0 if you go to the closure. Okay? Because polynomials are continuous, this also will hold on the closure. So this actually shows you that, well, I mean, I haven't showed that statement yet, right? But if you assume that for a moment, then this is a way of proving that that you cannot go from the W state, you cannot degenerate from the W state to the GZ state, because you have proved, you found something that cuts out the W state and have shown that this polynomial doesn't vanish from the GZ. Okay? Yes? Because I just allow, because I allow all limits, right? It's just because I allow limits now. I mean, I didn't formally do it now, but it's because I allow going to limits. And I mean, this here means allowing going to limits, and this here means allowing going to limits. Yeah, I don't want to spend too much time on that now. Sorry? No, because I'm going to the closure. So I mean, for instance, in the closure of the W state, I have the EPR state, and I can't go back. Okay? But I can go to the EPR state. So I take the boundary point. But when you take the boundary point, you know, then you can't necessarily go back. It's only that you can go back if you're really kind of like staying isomorphic here. You could kind of enlarge the statement here with restrictions, but I don't want to do that. Yes. That's correct, yes. Well, I mean, it's not necessarily open if something is not closed, but yes, it's not an algebraic variety if you don't close it off. And that is kind of, in that sense, I meant that things get easier when you do this closure business, because then you have somehow the tools of algebraic geometry at your hand to design these polynomials, yeah, and to cut them out. Yes. That's right. So 3 qubits is special in many ways, and in particular, the closure of the GHZ state is the entire space of tensors. If there were many mathematicians among you, someone would have remarked that the zero tensor is its own orbit. But we just, you know, who cares about zero tensors, right? So, okay. All right. So now we still don't know how we got to this beautiful polynomial there. All right. And I want to explain a little bit of how you get there, how you do it. And it's sort of also because I kind of like need the technique a little later on, spending a little bit of time on that. Okay, so basically we need to do some representation theory. And why do we need to do representation theory? Well, I defined a group for you here, the group G. Right? G was a group. So if you have a group, then you want to look at its representations. And you see that the polynomial that we defined here had somehow a nice property with respect to the group. So with respect to the group action, the polynomial was transforming in a nice way. It's called covariant, so it's like some covariant way. And if you took only determinant 1 things here, then it would be even an invariant polynomial. Polynomial invariant under that. And so representation theory kind of plays a big role here. And I want to, I'll tell you a bit about that. And it's really not very far from what you've learned in physics. Up to scale in this case, yes. There's only one polynomial that cuts out the W state, the W state variety in this case. But otherwise, if you have more polynomials, you could, you know, there may be different ways of cutting out the same variety of different polynomials. But this is sort of like the nicest and cleanest and simplest example, and things do get messy if you just even take 4 qubits or some high-dimensional system. But it's nice to have an idea of how the general construction for polynomials like that happen, because you see that the polynomials, this polynomial had a very special symmetry. I mean, had this covariance property, and in general, you can always make them happen, make this covariance property happen. So let's understand how this happens. I just want to make sure, you know, don't be afraid of this GLA, because you kind of know it. You know it because GL2 you know very well. GL2 is just SL2, right? And the representation theory of SL2 is kind of like, I mean, up to this determinant thing here, right? So up to some what people would call a scalar, right? So up to the scalar here in the multiplicative group with complex numbers that gives you the determinant. You really just have to play with SL2. And you know SL2 because the representations for SL2 are the spin representation. As like spin J, you know them very well. So what happens when you now take GLD, things get generalized a little bit and maybe more systematically, and then you take products of them, and then you have like products of spins. So life is not so different from what you're familiar with. So let me try to tell you how they're constructed. And they're constructed in the following way. So basically, if you start with GLD, you want to act, you want to think of, so maybe I first describe the representations to you, and then I tell you how we're going to kind of like implement the description of them. So I tell you first what they are. Okay, so for the GLD representations, I'm going to look at very particular representations. They're called polynomial representations. Has something to do with the fact that they're polynomial. Polynomial representations. But you can just think of representations. Oh, and you probably remember from your mathematical physics or so introduction that if you have representations and the group is kind of nice enough, like SQ or the finite group, then they break up into what is called irreducible representations. Okay? So it's enough to describe the irreducible representations. We're going to throw in this word polynomials, just forget about it, and we're going to look at the irreducible ones. Okay, what are they? Well, what you do is you say, well, these are a representation is some action on a vector space. Okay, so I'll give you some vector space V, and then I act with the group on it. Okay, so I'm so if I right, so what I have to do is I have to describe how. So this is a vector space, and you know, you can, you know, it's isomorphic to some CD. And now you act with the group on that in some fashion, and what is it? What do I mean by that? I mean that if there comes this group element along, and we'll just first study GLD, and you take a vector from this representation, from this space, then it will do something with it, right? And you know, so the representation, it will take V to GV. Okay, so and I have to tell you how it's done. Right? So if I give you a description how a vector V is transformed into some other vector G dot V, right? Then I have told you what the representation does. And if you have these things here, then actually there is a nice way of describing it. Namely, there turns out to be some unique vector. Well, no, that doesn't go up. There turns out to be some unique vector V that in this vector space there's some unique vector, and people call it the highest weight vector, that kind of like carries all the information that you want about that representation. It's called the highest weight vector. So it's like it has the highest weight. You know, it's the greatest and the best vector in this representation. And it's unique up to scale, so up to making it longer, and it kind of like carries this information. So for every lambda, so what is lambda? Lambda is some set of numbers, lambda 1 up to lambda d, where the d is this dimension, and the lambda i's, they are non-increasing for all I, and they are integers. Okay. Okay, for any of these set of numbers, and commonly instead of like writing it like that, people like to draw a diagram. They call it a Young diagram. So here's a nice Young diagram. Okay, that Young diagram, what is it in terms of lists of numbers? Maybe you don't know my convention. Okay, so this is like lambda 5. No, 2, lambda 1, right? 2, 4 has 6 boxes. 2, 4, lambda 2 has 4 boxes. Lambda 3 has 1 box. And actually, I'm doing it in 4-dimensional space. So lambda 4 has 0 boxes. Okay? Also okay. All right, it's called the Young diagram. This is the American way of writing a Young diagram. If you flip it on the diagonal here, then it's the French way of writing it. And I think if you, Leo must know. There's the Russian way of writing it, but I don't know. It's like some other way of tilting. Okay, so, all right, these are Young diagrams. And for every such d-tuple of numbers, you can find a representation, a reducible representation, And this irreducible representation will have this unique highest weight vector, V, I call it V lambda, such that if you act with a group on it, it stays the same up to the fact, oh, that's not quite correct. You're not allowed to act with a group on it. You're only allowed to act with, oh, this is not really, I shouldn't do that. We act with H on it, and H is a diagonal element, okay? So we chose at some point in the future, in the past, we chose a diagonal basis for our group, and then we have the diagonal matrices. And if H is such a diagonal matrix and we act with it on V lambda, then what happens is that what we're going to get is H1 to the lambda 1 times H2 to the lambda 2 times HD to the lambda D applied on V lambda. Okay, so it's multiplied by a scalar, by a number. Yeah, it's smaller. It's just the diagonal matrices. Well, it has the same kind of like dimensional, but it's just the diagonals. All right. So these are, okay, so now I promised you that this was not very different from what you already knew with respect to SU2. Of course, you could say, well, let me only plug in, let me take D to be 2. Let me only plug in things because I'm, I don't care about this phase. Let me only plug in things that have determinant 1. Okay, diagonal matrices, diagonal 2 by 2 matrices with determinant 1. They have the following form, right? The H would be like some H1. Oh, these are the diagonal elements, right? And then here it's like, yeah, hold on. Yes. Yeah, it's a vector. Okay. So for every, so it's, I'm not proving anything to you. I'm giving you some facts, right? So I'm claiming that for every lambda that you choose, there exists some vector space V, and that vector space has a vector V lambda, which I call V lambda, such that this is true. Okay, and on top of it, I claim that this representation is irreducible. Okay. No. For every lambda, you have some big vector space, and there is this vector V lambda, which will have this property, and in addition, it will kind of like be the highest one. So I haven't like specified that yet. It's the highest, it's the highest numbers here in some order, in the lexicographical order. But I don't want to go too much detail here. I just want to show you this little example because that connects to, I think, what you know. Sorry? Yeah. All right, but they have different weights here. Yes. So for this space V lambda, it's true. Okay. So this space V lambda actually, this space V lambda breaks up as a direct sum over W, and then it has some multiplicity space which we call CW, or K actually. They're called KW. Actually, K lambda W. Why not? These are called the Koska numbers. Okay, the Koska numbers. The Koska numbers. And then you have some, and then here you have some vector space span, and then here you could put a, we could call this V, we could call this W, WV, okay? And then this guy here, so in the lexicographical order, the highest one of these W's, there the VW is your V lambda. Okay? And in that case, because I said it was unique, the Koska number is 1. Yes. Well, we're going to come to Traval duality. For the moment, this is just a presentation. You could come up with it from many ways. This is just a presentation of the representation theory without actually having it told you how to do it, right? What I want to do though is I want to look at this case d equal 2, and yes. Yeah. They're powers, right? So H has like H1, H2, and H3, HD on the diagonal, right? And then H1 to the lambda 1 is this first number to the power lambda 1. H2 to the power lambda 2. Yes. Well, okay, so it's the I mean it's the maximal. I mean you take a maximal torus in your group G, and that turns out to be, in the case of GL, it's particularly simple. It's just the diagonal matrices. So they are the Cartan subalgebra. I mean the group, the exponentiated Cartan subalgebra. Yes. Yes, H is diagonal here. Yeah, so I wrote diagonal. So it's really just H1 up to HD on the diagonal. The rest is zeros. Yeah. No, the H is like you know, it has to do this here for all H. Okay. So under this action of this group, it will do its job. It will just look like that. Okay. So for every lambda, I can find some irreducible representation V lambda, which has a highest weight vector V lambda, little v lambda, and that will have the property, in particular, it transforms in this way. Yes. Well, yeah, I don't want to go much more into it. I mean, there are no others. I mean, so like V lambda now contains, well, the lambda kind of like, I mean, I can label this representation with lambda, and yeah, I can't make it more precise, I think. Okay, well, let me go to this d equal 2 case, because I kind of want to connect you to the spin business that is very familiar here, I guess. So so H is like, in this case, right, I take them determinant 1, so H2 is equal to H1 inverse. And then when I act on this, right, then actually it turns out that this that what you know as spin, okay, so we could just try to do that. Actually, well, okay, so here's the answer. If you take lambda 1 minus lambda 2, then actually this is 2 times what you know as a spin. Okay? So if you know spin J representation, then it corresponds in my language to a representation where lambda 1 and lambda 2, where the difference of them is equal to 2J. Okay? So if you think of this diagram box business here, then you know, you see that, well, this is lambda 1, this is lambda 2, and you know that J is a half integer, but of course the difference of the 2 is an integer. So if you divide that integer by 2, you get a half integer, and so that's 2J. Okay, so that corresponds to that. We can see in a moment how that appears in the construction. I want to spend a couple of minutes explaining some aspects of the construction. Well, this was something. The J, right? Sorry? The H. Oh, the H. The H. What does the H have to do with it? Well, you know that in this case, right, I can continue. Right. Okay, here we go. In this case, your V lambda is your ket JJ, okay? And you know how the diagonal matrices act on ket JJ, right? Ket JJ, that's right? You have a representation of J, and you label the basis states by JM. And the JJ is kind of like the highest one, right? Feels very natural because the M is kind of like ordered. So it's the highest one. And then how do you act on that? Well, I told you how to act on it, right? This way. And now you can like go through this. I told you what this is. So we can just try to do that in this case. So H applied on V lambda is equal to, and we do H1, right, to the lambda 1 times H2 to the lambda 2 on V lambda. And this is equal to H1 to the lambda 1. And then here, this was H2 to the minus 1, right? So it's minus lambda 2 of V lambda. But V lambda, I claim, was the ket JJ. And now you see that it's true because if you take, you know, I mean, if you know that if you act with the algebra, so your sigma z operator, that's the diagonal guy, and you act, you know, the normal one, you would write it like that, right? JJ, then you should all kind of like tell me now that this gives maybe J. J, right? It gives me this J momentum here, and depending on whether I half or not, it actually gives me J or 2J. And you see that if I were to exponentiate this action here, then actually what would come out, right, if I do T to the, no, not T, if I do H1 to the sigma Z, H1 to the sigma Z is actually just H, right? If I'm not mistaken, H1 to sigma Z is just H in this case. And then I act on JJ. This actually means that that I get H1 to the J out. And because depending on how you normalize this, you should get a 2 here, right? And then you get here JJ. And then you see that, because this you know, right? And then you exponentiate that action, you just get that. But you notice that I told you that J1, lambda 1 minus lambda 2 was just 2J. And you see that this formula is actually the same as that formula. Okay? So it just connects immediately to your representation theory of SU2. All right. What I was going to do before Graham interrupted me. Okay. I wanted to tell you how one constructs them. Okay. So here's how you construct them. And actually, it's not so unrelated to what Matthias told you about the Dicke states today, but let's not go into that. So you take n tensor factors of CD. Okay. This has a very natural action of GLD on it, and the action is just you rotate you apply G tensor G tensor G tensor G to it. Okay. So it's just that the action, it simultaneously transforms the basis in all of these local spaces. Okay? So GLD acts very naturally on it. And it turns out that if you now, it's a representation, right? But we know that representations decompose, yes, with the same element of GL, yeah. G, 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 G. Yeah. And so it's a representation of GLD. You know that this representation will break up into irreducibles if it wasn't irreducible in the first place, but it's not irreducible, so it will break up. And it will break up into this direct sum over representations lambda, and actually it will go over all of them. Over all of them with n boxes, okay? All of them of degree n, because I have n here. You can kind of see the degree. And then you have these representations, I call them V lambda, and then you have some multiplicity space, and I like to call this multiplicity space, you know, I don't know, square bracket lambda. Okay? And why do I call it square bracket lambda? Because actually this representation here has another action of another group, and that's a symmetric group. Because the symmetric group just permutes the tensor factors here. And the nice thing is that it commutes. This action of diagonally changing the basis and permuting the tensor factors, they commute. Okay? So you have an action both of GLD, but at the same time of Sn, so of this combined group. So actually, as you know, GLD acts irreducibly here, and Sn acts irreducibly here, and there's no further multiplicity. So this is called Traval duality. It's very nice. Traval. All right, good. It's nice because there are no numbers here, right? No multiplicities, right? That's why it's nice. Where are my notes? Here. Okay, very good. So now I promised that I could produce. So now it's the general description for producing polynomials that do jobs like this over there is to take is the following. I want to keep that, and I can't put that up, but I can pull this down. So what you do is you realize the following simple thing. You realize that CA tensor CB tensor CC tensor to the n is the same as CA tensor n tensor CB tensor n, okay, tensor CC tensor n. Okay. So you can do a Traval duality on all of those factors, right, with GLA, GLB, GLC. So this gives you direct sum into lambda A, lambda B, lambda C, V lambda A, V lambda B, V lambda C. And then tensor these multiplicity spaces, lambda A, tensor lambda B, tensor lambda C. Okay, so now we're ready, because what you can do is now for each, so fix now, okay, so now we're going to fix lambda A, lambda B, lambda C. By abuse of notation, I'm going to call it lambda. And then what you're going to do is you're going to pick a vector in here. Okay? So you're going to choose a vector V in here, okay, in the lambda component. Right? It's like choosing a state with definite spin. I mean, but with definite kind of like triples of spin. Think about it this way. It's like if you think of these lambdas as generalizations of spins, you have now 3 particles, you choose them with like the triple of definite spins. Right? Yeah, no, in the entire thing, yeah. It's the entire component. It's in this component, okay? Where I fix the lambda. Okay, I'm not indicating V lambda now because then, okay, but so now take this V lambda. Actually, you can take the V lambda to be a highest weight state, but never mind. Then what you do is the following. Here's your polynomial. You define P lambda, well, P lambda depends now on V, right? On your choice of V. Of T, you just take the dual of this, or the bra if you want, and then you contract it with T tensor n. Right, you can do it like this if you want. Okay, that's this here. Now, this is a polynomial in T. The polynomial in T of degree n. And I would say it's of type lambda. Yes? No, I just call it lambda. Sorry, I can call it like big lambda or something. I just want to have a faster way of writing lambda. Okay, so this gives you, this is a polynomial. It's a polynomial of degree n in T, and actually it will transform in some nice way with respect to the representations. I'm not going to demonstrate that now, but it will transform in a nice way, and because it's like constructed via representation theory. Okay? So we are kind of on a good track to our Kaley hyperdeterminant, and I'm going to tell you now what it is. Right? It should just be an example of this, and it's a very specific example. Namely, it's the following vector v, right? Now imagine you have, first of all, I should tell you what lambda is, right? What's lambda? Can someone guess what lambda is in this case? How many boxes does lambda have? 4. Excellent. Because we have degree 4, right? Yes? I'm sorry, say again. Yeah. No, I do Traval duality here with dimension A. I do a Traval duality here with dimension B. I do a Traval duality here with dimension C. And then I just group them a little bit. I group the GLs and the symmetric group things this way. And then you see, to actually kind of like you see here, I'm using, so Traval duality, so I'm using the right-hand side to talk about V, right? I'm using the left-hand side to talk about T, because I take T tensor N, right? And T lives in here. Yes? Yeah, it would give you something different, yes. Yeah, it has something to do with bosonic, but I kind of want to throw there's so many aspects to this. I kind of want to not talk too much about Sn for the moment, because it will just make things more confusing for a moment. But yes, I mean, if you took the one row diagram all in one row, then it would be corresponding to bosons. If you take them all in one column, it would correspond to fermions. But let's not talk about that because it would bring us too far off. All right. So Kaley is lambda, has 4 boxes, and it's this one. Okay. And what's the vector v? I have to tell you what v is. Well, I basically have to give you a vector in this triple tensor product space. I have to give you a vector that lives in, all right, in CA tensor 4, tensor CB tensor 4, right, CC tensor 4. Okay, so I'm going to do that now. It's like a 4 factor, and A and B and C are all 2, right? So just take the singlet. These are 4 guys, right? Take the singlet, tensor singlet. Right, for the first guy. Here you take tensor singlet. For the second guy. And here I'm taking it between particles 1 and 2 and 3 and 4. Here I'm also taking particles 1 and 2 and 3 and 4. And then I take the third one, the C space. I also take singlet, tensor singlet. And then but I have to do it differently. I have to do 1, 3, and 2, 4. Okay, so if you take V like that, and then you take V tensor 4, right? That's a nice polynomial. P box with this V is on T is that. And now you expand this. You should get the formula up there, maybe up to a scale or something. Yes. Yes, also, but not in a way I want to talk about now. It's an exercise to verify this. Okay. No. 1, 2, 3, 4, 1, 2, 3, 4, 1, 3, 2, 4. I think you can also take other combinations to give the same polynomial, but if you take them all to be the same, then it's 0, I think. And you see that you immediately see that it has the right symmetry from before. Because if you act on T here, right, then what happens is that you could, instead of acting on T, you could act on the singlet from the other side. But you know that if you act on a singlet with some matrix, you get the determinant out, right? So you use the fact that if you act on a singlet with A, with a matrix A, right, like A tensor A on the singlet, that's actually determinant of A singlet. Okay? So you use that property, and then you immediately see it has the right symmetries, and then you're done. You just have to verify the equations are the same. Yeah. Why do I choose n equals 4, L equals 4, or n equals 4? Because it works. N equals 2 doesn't work. It's 0. I think if you do the construction for n equals 2, it's always 0. 4 works. I mean, the theorem before just told you that this is a variety. It's cut out by some polynomials. And, you know, you got to find those polynomials. How you find it, that's kind of like a magic art. And, sorry? Yeah, I mean, you try, of course, to get the smallest polynomial possible, right? I mean, it's not so hard to see, I think, that the ones that are kind of like square, I mean, the ones that have the same number of row length, they're like the easiest. They give you invariant. They're spanned by singlets. They're easy to deal with. And you start with the first two. The first thing, if you were to do this bottom up, you would start with like the 2 boxes in a row, in a column, and you would construct all of this, and you would notice that it's 0. And you're kind of like, shit. Now I have to do, I have to do 4 boxes. You try that. Sometimes that's still 0 for some other spaces and not some other vectors, and you go higher up. Okay, but here it just was. Oh, maybe. Oh, of course. Right. I'm sorry for this. This is of course lambda A, and this is also equal to lambda B and lambda C. Right. You have to choose 3 of them. Sorry for this. I hope it didn't cause too much confusion. Yeah, you have to choose 3 of them. It's a triple, and the triple consists of 3 identical ones. That's why you see kind of like this is the highest weight state. This turns out to be a highest weight state for one of them, and the highest weight state for the next one, highest weight for the next one, and then you tensor them together. But things can get more complicated in other cases. They do. No, the GZ state is not is the entire space. There is no polynomial that will vanish on the GZ state, right? Because yeah, that's actually a way of showing that the closure of the GZ state is everything, because there is no polynomial. Sorry? Yeah, now you can start with the 0 polynomials. Yeah, I'm not going to discuss that. So, okay, all right. This method works for all number of particles. This method works for all dimensions, and this method will also work if your state has symmetries like fermionic or some other things. It's pretty general. All right, so now comes a new kind of like chapter, new topic, where we're going to use this tool that we just learned, this Traval Duality. And I want to, yeah, so I'm kind of like short on time. So maybe I should switch the computer. I think it's a good idea at this point to switch to computer. And then I can supplement it with Blackboard. I'm sure they'll have some questions. Oh my God, I have to make it big now. Okay. Hold on. I hope you don't see that. Okay. Can you try to switch? Well, I don't know. You just check. Okay, you construct a polynomial, you check its vanishes on a W state. That's it. Well, there are some theoretical reasons for this, but people call it because you can show that it's a so-called an unstable vector, and you know that on unstable vectors there need to exist rectangular like they exist lambdas that are rectangular such that they'll vanish on that one. So we kind of abstract nonsense tells you that for some rectangle it will work, but then you still have to find the rectangle. So you start with a 2 by 2, then you start with a 1 1, then you do 2 2, and then you see 2 2. Oh yeah, great, it worked. Okay. All right. So I have to just kind of make this bigger. I don't know how to do that. You know, there's this big stain in it. Okay, here we go. Oh, right. Okay, so the next topic is entanglement polytope. I hope I have the right notation for you, and this, of course, doesn't work. We'll just do it like that. Okay, so basically what I want to tell you now is some really funny, interesting, unexpected theorem, I think, that has to do with local spectra. So here's your tensor, right? I draw a cube. I call it T prime now. Don't worry about the fact that it's T prime and not T. Let's assume it's normalized for a moment. You know, we have our inner product. We're quantum physicists for a second. Thanks, Graham. I'm sorry for this disturbance there. So then you know already that we can slice it into matrices, right? So we can slice it in this way, and we can slice it in. And these were the singular values where you know, we could the singular values of this we're going to call lambda c. Okay, this is a collision with this lambda over here. It's not completely accidental, but we can call them lambda c, the singular values of this squared. Okay, so these are like the and actually these singular values squared, they're kind of like if you were to take this 3 tensor and look at the reduced density matrix, right, of like particle c here in this case, then actually these are the eigenvalues. Okay, so singular value squared, these lambda c's are the eigenvalues. Okay, and you can do the same for A, and you can do the same for B. Okay, so basically you slice it in these 3 ways. And then you can look at these singular values. Well, maybe we'll do that later. Okay, yeah. So you could think of this as I brought a little example, like illustration of this here from the classical world of probability distribution. This is like a piece of wood. Okay, so if you look at this piece of wood, it's kind of magical. It's not hard. Yeah, well, if you look at it from this direction, maybe these people here, maybe Graham already knows what he should answer. What do you see? You see a square? Yeah? See the projection is a square, right? Yeah? Okay. So you see a square, right? If you forget the 3rd dimension, just look at it. Okay, great. So yeah, I turn it around for you a little bit. What do you see now? Louder. Triangle. Okay, excellent. Okay, see a triangle? Yeah, you all happy? See triangle? Okay. What do you see now? Circle, very good. You see circle? Yeah, it's not quite true, but it's almost a circle. Okay, so but you see that somehow some intriguing. I mean, I can give it around, but please give it back to me. I made it for my daughter while I was on paternity leave. So it you see that somehow these projections, they can have intriguing properties, right? And it's a natural question to ask, given a triangle, a circle, and a square, can I find a wooden object that has these 3 projections? Well, we're going to kind of study this in the language of tensors now. And we're going to look at these examples. Let me actually see if I hope I did this right. So here's okay, I'm not completely sure what comes now, but so basically, if you now imagine that I start with the GHZ state, and I do this, when we go back to this here, right? Then you notice that if the dimensions are 2, 2, and 2, then and I have a normalized state, like these are probability distributions, I can actually, it's sufficient to specify one singular value, say the largest, right? Because they sum up to 1. So I have one number here, one number here, and one number here. And so for each tensor here, I can now draw a point in a three-dimensional, in like a quadrant, right? And I take always the largest, so they're always bigger than a half. So let me do that for the GHZ state. What is the triple of eigenvalues for the GHZ state? The largest one. Very good. Okay, what is it for the W state? Yeah, but I want the largest one. Two-thirds, right? What about the EPR state? Go ahead. Give me a guess. Someone, well, maybe a different person. EPR tensor product, right? Half 1 gram. Jackpot. What about the product state? 1, 1, 1. Excellent. All right. So if you take the GHZ state, actually, and the entire orbit, you see that you can reach 1, 1, 1. You can reach a half, a half, a half. That was obvious because I can degenerate to 1, 1, 1. I can degenerate to everything. I can also degenerate to a half, 1, and 1, a half, and whatever. And I can a half is down here. Okay, so I can get this entire thing. And surprisingly, I can get everything inside. Okay, so it's a convex hull of that. And there's no apparent convexity structure here. So it's really surprising thing that this is true. We call this a marginal polytope because it's like a marginal problem. You go to the margin. Now, if you do a subset, say the W state, and the entire everything the W state degenerates to, then the W state with its 2/3, 2/3, 2/3, it sits right in the middle of this plane here. Okay? And of course, it degenerates to the 0 and to the EPR state. We've seen that. So actually, you get the upper pyramid. Okay, you get this thing here. If you take the EPR state, one of them, you will sit here, and you can degenerate to the product state. You get this guy here. And if you do the other EPR state, you get this one, and you get the third EPR state, you get this one. The product state just gives you the point up here. Okay? So it's very surprising. These are actually polytopes, and one can prove that based on some algebraic geometry theorem by Briand. No, the W is the entire thing here. It's full dimensional, so it's this entire thing, right? From the W just sits here in the middle, and you can degenerate to these 4 points and to this one, and so it's the convex hull of that. So you can degenerate. You can get every point here in the polytope by playing around with the W state. It's really, I like it really. It's very sort of like surprising that this apparent like super complicated orbits with their structure and all of that, suddenly they give us these nice geometric things. I even have some of them built at home. Okay. And you can use it for experimental detection. This is for the experimentalists. Do this in your lab, right? Take your quantum state psi, measure these reduced density matrices, the single particle measurements, like efficient to do even, you have your n particles. Then check where it lies in the polytope, right? And if it doesn't lie in the W polytope, then you know you created a GHZ type entangled state. Very cool. If not W, then you must be GHZ. So we're very excited about this. It's an easy test for entanglement. Our referees were excited too. So we got into science. If you get a paper into science, maybe the experimentalists know that, then you can make a proposal for the cover page. This was our proposal for the cover page with our nice polytope and some size here. Of course, it wasn't accepted, but nevertheless, but I think it's kind of nice. So anyway, so just that's some gibberish here. Headline. Okay. All right. I'm not the only person in this country that likes it. I have no idea. I never looked at it. I don't know. All right. Yeah, people did it actually already. You can still do it, you know, maybe for bigger numbers. So people did it. This is an optical setup here, and they showed some data. There's some, you know, okay. A little more partial information. But I should emphasize, this was only partial information about these orbits, right? This is nice geometric information, but it's not the complete information. And so the question is, how do I get more information? All right. You've seen that before. Maybe we had this. Oh, yeah. So, sorry for this. Yeah, this polytope has a different description. This is like really weird. So I could also say, let me consider all the lambdas, okay, for which I can find a vector on which it doesn't vanish, right? You've seen one. You have seen the square, right? If you now take the square, if you think of this square, the 2 by 2 square, and if you think of this and you normalize the row length, right? Then, right, it was before it was 2, 2, and now you normalize them to sum of, so that they sum to 1. What do we get? A half. And alas, and it doesn't vanish on the GHZ state. So it turns out that it has some kind of dual information. So this kind of diagram that you get, if you normalize it, then it's exactly this stuff that doesn't vanish on your tensor. It gives you the same polytope. You go over all the lambdas, you normalize them, they don't vanish on your T. It gives you the exact same polytope as the polytope that you got by looking at all of the states in the GZ class and looking at the reduced density matrices. It's kind of thing. So this polytope here is like two non-trivial descriptions. One in terms of like the representations, these lambdas, and one in terms of like the reduced density matrices. And this is very important, this duality. Right. So, all right, here it is. I took a picture. Do you see this? It's sort of like you can shine light in from 3 directions, and then you see the three reflections. It was kind of difficult to get my wife to hold the lamp, but anyway. Right. All right. Let's return to main question. The main question we wanted to talk about was, when does T degenerate to T prime? And there is this small observation which we had already made, but for the people who saw this talk, I had to make it now. Namely that the EPR to 2 to the n, you know, it's in a different notation, but that the MAMO is the MAMO 2 to the n. Okay, it's like this observation that we had. And yeah, here it is. Okay, see MAMO D, where D is 2 to the n, is MAMO 2 10 to n. Okay? That was just for this the small observation. And so this kind of like leads to the question, very natural question. I'm going to just talk about it in 5 minutes. When can you do this restriction asymptotically? So when does T tensor n degenerate to T prime tensor n? And you know, it's motivated because in quantum information theory, we would like to kind of like have many sources, and you know, we do some coding and we get something out. So it's a very natural question. And in algebraic complexity, it's also very natural because you don't want to multiply 2 by 2 matrices. You want to multiply 2 to the n by 2 to the n matrices. And so you want to kind of understand that. And it turns out that that this exponent, so it turns out that Strassen's algorithm for 2 by 2 matrices. Okay, so Strassen had this decomposition for 2 by 2 matrices, right? And you know that if you multiply 2 by 2 matrices, you need how many multiplications? 8. Okay, so you need 8 multiplications. Well, Strassen's decomposition allows you to do it with 7 only. Okay, so multiplying 2 by 2 matrices with Strassen, you can do with 7 multiplications. And so this would still have been boring, right? People would have said, okay, fine. I mean, Strassen, now you can multiply 2 by 2 matrices with 7 instead of 8, but who cares? But what it actually does is you can iterate this. Okay, so you can do it like it works on block matrices. Okay, so you start with your 2 to the n by 2 to the n, you make it into like 4 blocks, and you do this on the blocks, and then you do it on the next level, and so on. So actually, Strassen's thing, Strassen's gives you an algorithm it gives you an algorithm that, you know, like normally if you do D by D matrices, you need like, right, D multiplications for every outcome, so it's D cubed, right? It's D times D squared, which is D cubed. That is your high school algorithm. And Strassen can do it in D to the log 2 of 7, and log 2 of 7 is approximately 2.8. So this was the breakthrough, that he managed to show that you can multiply matrices better with better than exponent 3. And people have improved this, but that's not so relevant. But it's still open, whether or not you can do it in exponent 2. It's actually a very interesting open question. And in our language, this just corresponds to the following question. It corresponds to the question whether I can, this is called my symbol for the GHZ state, whether you can degenerate, whether you can restrict a GHZ state of, you know, the of size 2n to the MAMU. Okay. So the exponent is the smallest r, such that you can restrict from a GHZ with nr to the MAMU tensor n. And the question is, right, the question is now in our language, you know, can I restrict the GHZ 2 square, right, 4, asymptotically, that's my symbol for asymptotically, to the MAMU 2? No, like for n large enough, right? It's like a little of n here, some fudge factor. Yeah, we'll give you a finite. No, but you cannot. Well, I mean, it's an asymptotic definition. That's omega, right? So people are really interested in that, and the conjecture is, well, here's the conjecture that you can do it with 2, so that, and that would be really cool to prove it, but no one knows how to do it. And so what we did, kind of like we studied this asymptotic restriction, right? We studied this notion of when, or Strassen studied it already, when does T restrict to T prime? And we say that T restricts asymptotically to T prime if it restricts to, if T tensor n restricts to T prime tensor n, so like for large n. And that's sort of like the question. And you can again start like the GHZ state here. You can again take the GHZ state and you can build like some rank. You can do like this asymptotic rank. And this here is sort of like the asymptotic notion of rank, and maybe it's more familiar to take a log. And you can study the asymptotic rank of the MAMU, then would exactly characterize your exponent. And you can study the asymptotic subrank, and so on. So we've been playing around with this. My time is up, but we found some nice functions that kind of like are the analog of these polynomials. So you would kind of wonder, are there, I mean, can I do the same thing? Can I decide asymptotic restriction? Can I decide it as nicely as I can decide degeneration with help of, say, polynomials? And Strassen had a nice theorem there that in principle that's possible, and but he couldn't really produce any of these functions, any of these polynomials analog. And so what we did very recently was kind of like construct them. And actually the functions are very simple. So I can just tell you what they are, because I can just tell you what they are here. Because the functions, maybe they look complicated, but like they take the polytope and you just measure the distance to the origin. Okay? So basically these functions that are the analog to the polynomials for this asymptotic restriction, they're the distances to the origin here. And you can quantify this distance in different ways, and these different ways give you different functions. But in all of them, they're kind of like a natural set of functions to consider, and there's some definition up there. But maybe what is nice is that they are kind of like built on top of this entanglement polytope, and they give you this information. So I think with that, I'm kind of done. Maybe you have more questions. I guess with, I'm not sure if I'm good to answer. I guess with polynomials you can also localize points is good. I'm not sure if I can answer. Maybe I have to think about an answer later. Maybe. Yes, but so like with polynomials, you can separate points in the normal Euclidean topology. So I think that's maybe the intuition.